Okay, why don't you go ahead?
Okay, so yeah, so I'm looking at this thing, and so in general, the boundaries for some couplings like a q k to a q1. So in general, this is going to be something like this. You have some function here, and then another one, and then like different regions. So like 1, 2. Which basically depend on the number of states. So if you have an infinite number of states, then you have an infinite number of these boundaries. And of course, if this is equal k, then this is just Obitope. Yeah.
But when you have section, usually when you have like the first function, the second function, and the third function, each of these function corresponds to different number of states, or what do they correspond to?
Sort of. So if here is a plot for n states, then I will have like n of these such boundaries. If you give me a different number of states, then in general, the boundaries all of these boundaries might be different.
So first of all, when you give n, so you're saying give n states, there's going to be n boundaries, and the precise form of these boundaries will depend on the state, on the spins of the n states, right? Depend on the j of these, and the different j you choose will lead to different boundary, right?
Yeah.
So when we take into so then how, I mean, how precisely are you like getting the, so you're going to have an analytic bound when n goes to infinity?
Yeah.
So how did you achieve that?
Well, in some cases, these boundaries are finite even when you take n to infinity. So in some cases, the boundary might go to 0 here, but other times it's just converges to some finite value when you take n infinite. So it depends on what couplings you're looking at, but if here I have, say, n equals infinity, then this might be, the boundary for n infinity where I have like integer spins or something.
So basically, you're saying that these boundaries, you have an analytic formula for these boundaries, and it's analytic in terms of, okay. So it's okay. So maybe we can go through these formulas.
Yes. So this solution is for the first boundary. So it's always like the first one that appears, where all of the row xi are given by this. So it's L on this interval, where x1, so these, I'm assuming that you have x1 smaller than, so it's like this. Yeah, so then this is the first boundary solution. Then the next one, if you want to go to the next one, the second one, that's going to be the first row x1 is L on 0, 1. So it's like full. And then the next one will be something like that. X2 will be L on 0, M, and then some value there.
Sorry, so
and then you go.
Right. Sorry, so my x is supposed, I'm supposed to see x as a spin.
Yeah.
So
here I list as xi, but in general, xi would just be I or something.
Okay. And
or n is one over z or z here.
Sorry, who?
M.
M. This M is just some other parameter.
Okay.
So what is that parameter?
So this is the parameter that moves you along the boundary. So as you increase M, you're moving around on this boundary. Right? So it's like a 1D boundary, so it needs one parameter. Because I will get the couplings as some function of M, right? So A1 a function some F1, and A2 will be some function 2 of M. So then I do a parametric plot in terms of M. So this gives me some curve. So basically the parameter comes from where a row has support.
Okay, this is really engineered for some 2D thing, right? This is only for 2D, right? Because this is by definition, because yeah.
Yeah, for a 3D thing, you'd have something with the 2 parameters. You'd have, so here, all of the solutions are of this type where you have, so rho of z is some step function like this, and this is m. And then if you want a 3D plot, then the row will be something like this. Where now you have M1, M2, there is 1.
Mhm.
So this would be the solution for a 3D plot. Then you get a surface.
Okay.
And you can check that using these solutions, the respective Hankels vanish. So if you use a 2x2 Hankel, then it vanishes when you have something like this. If you use a higher Hankel, then you need something like this to vanish and so on.
Okay.
So this is basically the equivalent of for the old geometry where you have a number of states, right? If you want a 2x2 Hankel to vanish, you need 2 states. Then you have to increase the number of states as you go to a higher Hankel. And higher Hankel means like a higher degree boundary, higher G. Yeah.
Okay.
Yes. So here, basically, so the general claim is that for this problem where you have one is on 0, one moment is 0, 1, and the other is discrete, the solutions are always some step functions like this.
Uh-huh.
It's just step functions. It's never some. Yeah. Okay. So yeah. So then you can. This is easy to derive actually. You just start by assuming 2 states. So actually, maybe I should write this in. You just assume 2 states. You have 2 parameters. So let me write it down. So I assume right? So I just assume 2 states, and then I use the fact that rho 1 of z is going to be L on some 0 M1, and then rho 2z is going to be L on 0 M2. So I know this covers the whole possible space of this space. And then I assume that M2 is going to be some function R times M1. So this is an assumption. I don't have any way to justify it, but this is what works. So you assume this, and then you just plug these solutions in here, and then you minimize, and you find that the z.
What do you minimize?
So I compute. Say I want to look at the plot of a K2, Q2 versus a K1. So then using these solutions, I get this is some function of M1, and this is some function 1 and Z. And then basically I want to find the lower boundary. So then I just minimize over Z to see where this, how to get the lowest.
Sorry, are you in this whole construction, are you already assuming that K2, that K2, Q2 is bigger than K1, Q1, or is there some hierarchy between? I mean, because because what is lower boundary, it depends on what is the I can flip the XY axis, right? And then so how is this information coming?
Yeah. So I'm always assuming that the K2 is larger than K1.
So is that the criteria about which is it determined by K and not Q, right? So what is it?
Yeah. Yeah, so this, and then you always want the Ki larger than Qi.
Okay.
So you just plug in these solutions into the 2AQ, and then it's easy to minimize, and you just get that this is the form you want.
And then you check by doing numerics and
then I just allow the rows to be any functions. I generate random functions, and then I compare, and I see that this solution is always on the boundary.
I see.
Okay, so yeah, so you get this, and then once you have that, let me just get rid of this. So then you can go to the physical couplings, which are now given by this. And you can do the same thing. You find that the boundary is given by the same type of solution, but now you use xi is L plus L, so it's just J squared. So then you just plug in the solutions into the AK, you can do the integrals. And so for example, if you look at these two, you get just this. So that's a parabola, which is this thing. And then from the polytope, so the polytope for A42, A41, we already know the exact formula, and it's some polytope, right? And then this you intersect with the null plane, which is like so this gives upper bounds for A41, A42 here, and for A41, right?
Sorry, why is the null plane a line in A42?
Well, this is just the null plane, right?
No,
Just
I
a
mean,
line.
here you're figure 8, you're plotting A20 versus
Yeah,
A42.
this is just, yeah, so here it just means this is the upper bound. So from here, I know that A42 has to be bounded here. So it's somewhere in this region. So then I'm just cutting off here, so it can be anything in here. And then you get the maximum for A20 here.
So here, this is so this is sorry, so this is I mean, what are you taking to infinity now? I mean,
oh, sorry, I just skipped here. So so I take the solution. Oops. So I take those solutions for rho. I plug them into some AKQ, right?
right.
I do the Z integral, and so I get some simple factor like this thing here, and then some extra thing here. And then if these numbers are right, this sum converges, right? So here, this sum goes like, so in this case, I get this. So it's like 1 factor of L here and 4 downstairs here. So it's, so the sum is like 1 over L cubed. So this converges. Right, so I just get that A20 is given by some finite number times my parameter.
So you get a zeta value? Sorry, do you this sum actually gives you a zeta value?
Yeah,
you just plug in Mathematica and you ask it to do the infinite sum.
Yeah. So yeah, so then it depends on all of these variables when the sum converges. But it seems like usually it converges. I mean, yeah, it depends.
I see.
So for example, A20,
I see.
this converges, but A20, A41 doesn't converge.
I
But
see.
this is in get some bound. Yeah, so then, yeah, so this is where you get the upper bound for A20, basically.
So this,
And here,
no, continue, sorry.
yeah, so just here's where the boundaries actually come into play. So this was just the first boundary, which terminates here, right? And then from then on, you have the second boundary, which is this green thing, just slightly different parabola. So then to get the exact intersection, you want to figure out this boundary, which is not hard, but I don't have it yet. So here I just do the intersection with assuming I just get this. So
Sorry,
that's why I guess.
Sorry, but this looks like the first boundary. Okay. So do you know where the point that the first boundary and the second boundary, I mean, so what is the meaning of the first boundary and the second? Is just meaning that, well, what are the number of states? I mean, sorry, I'm not, what is the meaning of the?
Well, you have different types of solutions.
Yeah, how
I
do
mean,
yeah.
Yeah, so I don't know the exact motivation, but the thing is, if you just do the plot like numerically, you find that there are different boundaries. And then each type of boundary, you know analytically where it comes from. So it comes from different types of segments for the row J's.
But how do you differentiate between the different? Yeah, I mean, so so let's say, I mean, you're doing the first boundary and the second boundary. So what is so what is the characterization of these two solutions? You must know, right? Because you're doing extrapolation.
Yeah. So the first boundary is given by this formula, right? Where you have this is Z. So all of these things are some segments. Then the second one is the first row for the first element. So like row 1 would be L on this segment. So it's like the full segment. And then the next one will be something like M and then some function here. And then row 3 will be L on 0M, something like this. So this would be the second boundary.
So as each boundary go higher, you just mean that there's some more and more of these row are becoming full boundaries.
Yeah, exactly.
But these rows are like, for example, you write row 1. So does that mean it's a spin 1 that is going to the full boundary?
Yeah, it's the first element. So I mean, so this is X1. So this could be anything.
Right, but we're extrapolating, right? So this has to be well defined in the extrapolation.
Well, I'm just extrapolating to get some. I mean, I don't have to extrapolate. This is just to get some quick number.
Yeah, but but only, like I said, only the extrapolation is I mean, any finite thing is not going to be at any true boundary, right? I mean, you can violate these finite things just by having things whose Hall is not these elements, right?
Well, here I'm including all elements because so I'm summing over all spins. So there's no new element you can add to the Hall.
Right. So then, what is X1 then? Spin 1 or is it spin 2?
Oh, yeah. It's the first element in the set.
Okay, so then it's spin 2, for example, or is it spin 2 or spin 0?
It's actually spin 1. Yeah, there's no scalars yet. So it's spin 2 because it's a permutation invariant. Okay,
so it's spin 2. Okay. So basically the different segments are associated with more and more of these lower spins are becoming full range.
Yeah.
That's the characterization. Okay.
And the picture is the same as you get in like a 2D moment, both continuous. It's similar to this, right? So initially you have some circle, some disk that moves out, but then at some point you reach the boundary, the upper boundary. So then some of the region is fixed at 1, and just the others that change. And then basically when you have discrete, then basically you're looking at lines here, right? So in the beginning you have some disk that intersects all of these segments in different points.
Mhm.
But as you go higher and higher, some of these have to like be all the way to 1. And just the followings that have some function.
Cool. Now I see what's okay. So this really the only mystery here is just why is this the boundary, right? That's the only. I mean, so all of these analytics is just straightforward. I mean, sorry, and I mean it's straightforward in the sense that yeah, you can just once you assume what are their segments, then you can solve for. I mean, yeah. So the only question is yeah, why is this seems to be the okay? So what is it? The statement that you said compared to Simone's?
So if I used this extrapolation, I get something slightly larger than Simon's, but that's just because I'm not using the actual boundary. I assume if I use the correct one, I will get exactly this.
You mean the second boundary? So right now you're using the you're saying that you're using the red one, which gives you 0.7. So if you get the green one, you'll get the 0. Okay, I see. Okay, I see. Cool.
Yeah, so actually this matches exactly what Simon was doing. So in his sum, for him basically,
he was spin 2, right? He was doing the spin 2 that was.
Yeah, he had the scalar, but we're ignoring that spin 2. And this had the range from 0 to 1, right? And then it was 4, 6 that had the 0 to some Z max. So in this sense, this is exactly what he's doing. Of course, I don't know how the fact that he's adding the null plane, how it's related to this picture, but otherwise.
You're also using the null plane, right?
Yeah, I'm sort of intersecting. He's adding it as some free parameter.
Yeah, but then yeah, it's probably. But anyway, but I'm just saying, information-wise, it's the same thing. The information that goes into determining these bounds. So I guess right now we're slightly at a disadvantage. So this is nice. So we have a systematic way of pushing this to any coupling that you're interested in. So and we can actually do this for arbitrary dimensions, right? All that's going to change is just that the Gegenbauer polynomials in terms of these J's will be different.
Yeah.
But roughly speaking, there you can do this for arbitrary dimensions. Okay, cool. So I guess then, besides the explicit analysis, what we really want is we should really try to think about deriving some or understanding somehow why these are the correct boundaries, right? And of course we can use the 1D as an example and use the 1D to the with the 1D moment as you say as a motivation for this kind of bounds. But it'll be good to just derive it. Okay, so I think that so actually, sorry, did you want to say something?
Yeah, so I mean, before we start thinking, I think trying to derive these exact boundaries of like the blue one and the green one from Henkel's or anything like that, this might be too much, because I think this will be similar to the old geometry, right? If we wanted to plot something like this, I think, well, of course, now projective in some way. I think you also get different bounds, right? Instead of the polytope, if you're doing different k, it's going to be slightly curved.
Mm-hmm.
But like each boundary of the polytope gets curved in some way. So you end up with something with many boundaries. But we never knew that, right? And we still got the right answer.
Uh-huh.
So in that sense, it might be too much trying to derive this exact boundary. And we might just need some general like Short's type inequality that doesn't have like doesn't matter how many states you have and things like that, just like for the old geometry.
Sorry, in old geometry, I guess you're really talking about, sorry, I guess you're really talking about our mindset in the early days. So before we had this generalized Hankel. You're comparing to that stage? I'm a little bit confused about, yeah.
Yeah, so just ignoring the generalized Hankel for now. So the main constraint we had was something like a Shor's inequality, which was just the Hankel of maybe the diagonal, right? We had some constraint like this.
Right.
And then we had the polytope and all of the other stuff. And this
Right.
is all you need, right? So excluding to get the precise boundary, this is enough. But of course, if you want to plot, yeah, so here the strange thing is it looks like you have all of these infinite boundaries that are different functions and so on. I think that was also the case here, it's just that we didn't care about that. We just put all of the conditions together and that was enough. And none of the conditions was something complicated. So here I'm wondering whether there is something simple and similar to just the Shor's inequality. Then once you just project out stuff, you end up with these solutions.
Yeah, I mean, that's in terms of, yeah, okay. I mean, certainly that's in terms of, you're talking about how to understand that these curves are the correct, I mean, these boundaries are the correct boundaries. You want to avoid talking about what are the states on those boundaries.
Yeah.
That's basically your point. Yeah. Yeah, I guess we can, once we have it set up, I mean, sure, we can see which way is more promising. But anyhow, but Lorenzo, I think right now you have just by, okay, before we go on, so Yuan and Hudson, do you guys have any questions you want to ask about what Laurentio is doing? So do you guys know what he's doing, right? He's assuming that he's first starting with assuming that the Hall is given by a particular states and the boundary of those states, he's deriving the boundary associated with your Hall is just comprised of, and then he adds more and more elements into, and then you can extrapolate, then you can, so once he add more and more elements, and then he is extrapolating when you have the complete set of elements in there. And so really the issue here is, as I mentioned, that why, I mean, you could, why is it that it's these particular spectrum that is saturating the boundary? It's kind of interesting that we're actually now in this picture, we're actually knowing the spectrum first. We're actually plotting the boundary associated with the we're assuming that we know so it's like completely opposite of the previous case, right? We've spent a lot of time figuring out what the spectrum, even though we already have the space. Here we're first identifying, so identifying what is the boundary spectrum, and then plotting out a space. Okay, so I guess you guys don't have any questions?
Sorry, I'll be right back.
Okay. Anyway, so maybe it's a good time to probably organize this like in the draft. So maybe Laurentio, I know this is probably pretty rough. So maybe you can have like a you know, just a motivation, like you do step by step, and then just write out the conditions, and then we can start thinking about, so of course then we can split up the task in terms of analysis, what combos to do, and then also think towards what exactly, I mean, do we have further justifications for, I mean, like I said, we already know there's a 1D justification, right? Because that is we have the 1D proof. So in a sense, this is a generalization of the 1D problem. But we would like to understand, why is this a proof that this is the boundary value? Right, and then, so maybe it'll be good, yeah, so maybe if you can write these things in a more detailed in the draft. And then we can spend like a day or two going over it, and then maybe we can then meet up again, and then you know, and then like everybody take their piece of the pie to do the analysis. And then we can focus on the analysis part. Yeah, okay, that sounds good. Plus, and Yuan, do you guys have something you want to discuss, or?
Yeah, actually, I was
Um,
thinking about something after I took a look at Hudson's new boundary for the spinning external states. So the space after Hudson has imposed another null constraint, which he called null 2,
Mhm.
the space has shrunk to a region that is very close to like a triangle shaped region, but yeah, strictly speaking, it's not a triangle, but yeah. So
By the way, I think that space looks a little bit familiar with the photon scattering space.
hold on.
Is that similar? Do you
Oh,
guys know?
sorry, I don't know how the photon space looks like.
I think I kind of feel like that space looks a little bit similar. So let me just call the. Sorry, just give me 1 second. So I'm just mentioning this. I guess you guys are. I guess are you guys doing gravity?
yeah,
H equals 2.
Yeah. Okay. Yeah. So I suspect that if you put H equals to 1, the space that you're going to carve out looks like the photon space. So sorry, just 1 second. So let me just find the paper. Sorry. Okay, so let's just, I remember that the paper was citing us. Okay, not yet. Probably it's the other EFTT paper. Yeah, this rigorous bound on light by light scattering. Yeah, I kind of feel like the shape that Hudson was showing me was a little bit like what they have in this paper. So they're basically doing the same thing, but with Simone's, which is basically what you guys are doing. Yeah, let me just take a, yeah. So this is the shape that they have. I kind of feel like this shape is a little bit like what you guys have. You know, because you guys, it's not really a triangle, right? Because it's really some, or maybe,
yeah, it's not fun.
do you feel it's a little bit similar?
Oh,
Or maybe you can. Well, I mean, later on you can do
Yeah.
photon and compare to their shape.
yeah.
Okay.
But anyway, but okay, sorry. So continue.
Okay, so I was thinking that because the final region that Hudson has carved out really looks like an intersection of two polytopes, right? So actually, we can think of the global analysis in this way. So first, we have some dispersion relation for the plus minus amplitude, which may just call it M1, or okay M1, and it's okay, maybe MB, and the coefficient and the Wilson coefficient associated to it, let's call it BKQ, and we have another dispersion relation for minus plus minus helicity configuration. That's called the Wilson coefficient C. So basically, the null constraint is a linear map between B and C, right? So first, suppose we have some geometry for B, and also we have some geometry for C, then it's simply asking that, okay, so we can first carve out the space for B and C respectively, and we do some linear transformation on C, and we ask what is the intersection between these two spaces. And,
Right.
and this is the final region that Hudson has.
Yes.
So the very fact that the space actually shrunk after Hudson considered the null constraint, null 2 constraints, actually implies that the geometry for C cannot be trivial. It means C cannot be unbounded. It must have some non-trivial geometry. But
Yes.
the dispersion relation of C, it's actually not easy to see that what kind of geometry it has, because it's not simply a positive sum of, it's not the original
Yeah, that's
moment
alternate
problem.
sum, right?
Yeah, -1 to the power of L.
Yeah, yeah.
So even so it implies that the STP result simply implies that even if we have this alternated sum, we still have some geometry, yeah, non-trivial geometry. I'm not even sure if it's a convex hull or even a moment problem, but maybe it's worth to like investigate the geometry of the other amplitude MC with -1 to the power of L.
Maybe, sorry, I didn't catch a final sentence. Maybe it's worthwhile to do what?
Worthwhile to investigate the geometry
Oh,
when
you
we
can
have
just
this
look at that
alternative.
sector and yeah, that's indeed kind of mysterious, because you don't really have a convex hull in that sector.
Right.
And we actually when we're at fixed K, yeah, I agree. When we were at fixed K, we looked at that sector, and it was obviously that sector did, for fixed K, that sector did not, was unbounded. That sector for sure is unbounded for fixed K. But He-Tsen, are you imposing, are you looking at these constraints you're combining various K, right? Up to K.
Oh, no, only K equals 4.
You're only doing K equals
Yeah,
4.
only K equals 4.
That's weird, because I remember that we did fixed K and we found that there was no bounds at fixed K. So there was no, because fixed K, you only have polytopo. I mean, these are just polytopo stuff, right?
Yeah.
So at the time we looked at fixed K, we didn't find any bound. I think it's more, I think it's,
But the larger boundary is given in the old paper, right? It is a closed region.
no, the whole boundary only, the bound, we were only able to bound plus, plus, minus, minus. We were not able to bound plus, minus, minus, plus, because as you say,
Yeah,
that
yeah.
geometry is, yeah,
Mhm.
that was unbounded. I mean, so what is the dimension? So K equals 4. So what is the dimension? Is it through, is it 3? Is it P2 or P3? It's P2, right?
Yeah.
It's,
Yeah.
it's 3 coupling with just 2 components.
Yeah.
P2,
Right.
right?
Right.
Yeah, that's weird, because I remember it was, I mean, it's pretty obvious, because you just, all you need to do is just look at the vectors that you get. And then you see that the vectors with the, you see that the vectors have plus and minus signs where you span the 3-dimension space.
Yeah, but if it really spans this 3-dimensional space, then
There shouldn't be any, you should.
yeah, the intersection must just be the space, the original space itself, right? So
Well, yeah, there's something fishy, but maybe you guys can take a look. But I remember that there was no, I mean, sorry, He-Tsen, can you just immediately just show us the vectors associated with different L's in one of these? I mean, we could just look at the vectors. Like from 1 to 10, maybe just list the vectors for L equals 1 to 10.
yeah, we have just done that before the meeting.
Oh, you just done that?
Yeah.
Wait, let me type up code. Okay. So this is
These are the vectors.
yeah, this is 4, 0, 4, 1, and 4, 2.
Oh, this is interesting. You're either all minus or all plus. Sorry, well, why is it?
Yeah, because The minus sign is, yeah, it's -1 to the L, so it depends on the even or odd on the spin.
Is there an S minus, is there an S minus, but you have S and U, right? So sorry, is this just
Yeah.
expanding, this is already coming from expanding the,
The whole and
Yeah,
the-
S and U channel, yeah.
Yeah.
S and U channel.
then this is weird. Because this is, so your vector is either living in the first quadrant or the, in the 3-dimension space is either, or the diagonal quadrant.
Yeah.
Doesn't that mean that you're spanning the whole space? Yeah, I agree. You guys should, maybe, yeah, you guys should, sorry, so this is, we're factoring out the prefactor, right? The prefactor is factored out.
Yeah.
Okay. Yeah, actually, yeah, maybe Jose, just to make sure you're doing the correct thing, maybe you can do the photon thing and then make sure you match with their result.
Okay. Okay.
Yeah, that'll be, that'll be, but okay, but, okay. Yeah, I agree. It'll be, but for some, yeah, for some reason I remember, and also Zvi agrees that there's no bound. So it seems like a contradiction. So they actually, if you look at the Zvi's paper, they actually say that for fixed K, the minus plus plus minus have no bound. They've actually tested it. I thought that you were looking not just at minus minus plus plus, but also the all plus and all minus and combine everything. So you're not.
No, only.
But for the all plus, we don't have we don't have a null constraint that connects this with 2 plus and 2 minus, right? No crossing that relates them.
No, they're not, but they're right. But I just in the sense that both of them have to satisfy the same. It means using the same couplings. That's what I'm saying.
Yeah.
But anyway, you guys haven't started using that yet.
But if there's no crossing that connects them, how can one affect each other? I mean,
But aren't they using the same coupling?
yeah, they're using the same coupling, but they just don't talk with each other, right?
I'm not sure about what, I mean, we're talking about bounds, right?
Yeah.
So why do you say that they don't talk to each other? If the couplings in one space is constrained by, yeah, I mean, it's just like the, I mean, I guess once again, it's just like the, it's just, I mean, here it is just like the C square is bounding D, right? I mean, the thing that we discussed before. Right, the thing that we that's about multiple species. Right, so we have like CA, CB is bigger than D square, where D is the couplings that you guys are talking about now.
Right.
So I think the very fact that you're saying that these don't talk to each other is precisely that. Once again, it goes back to the original problem that so far we don't know how to derive those bounds yet. Right, I mean, it's because those bound reflect the fact that those bounds CACB bigger than D square, assuming that you can obtain the full thing. That bound corresponds to the fact that they're using the same couplings, the same 3-point couplings, and that's why I say that these two should talk to each other because they're using the same couplings. But the fact that they're using the same couplings don't appear in your relation. Probably, yeah. So it's the same problem we had before. But yeah, look, we should look into this. So I think right now this is really now becoming a separate. Let me think. Yeah, this is a completely separate problem than the. If
Oh,
we don't
that's-
have a, I mean, sorry, if we don't have a moment problem, if we don't have moments, so here we don't no longer have moments, right? Yeah, here,
Hmm.
so I'm just thinking about whether or not this project can be still combined with what Laurentio is doing. In other words, can we further include the constraint of P is smaller than 2, for example? But does it, so here, so right now here, we're just literally using SDP and working on this, and we're not using any geometry.
Yeah, only a CP.
Yeah, and we're not using, and I mean, of course we can attempt to, but the point is that, right, the point is that if we try to use frame it in terms of geometry, the different spins are all, the different spins are all, because for example, in minus minus plus plus, the S channel and U channel polynomial are different, right? So basically you're already having two different geometry. I mean, this is different than before, because previously the S channel and the U channel still share the same polynomial. But now
But
even
it's still a sum of convex hull.
sorry?
Oh, but it's still, we have two different geometries, but it's still a sum of two convex hull. So we still have a positive geometry, right? So
Yeah, we still have a geometry, but we don't have, I mean, it's not in terms of a single moment, it's not in terms of just
single convex.
some
hull.
double moment thing, right?
But I don't think that's, I mean, it's just, you just do the sum, right? If you can do each geometry separately, then you just add them up and you don't need to do anything else.
I think it simply implies that we have to do some more complicated rotation to bring it to the A geometry, which is simple. When we have two positive sums rather than just one.
Yeah, that's probably the truth. Yeah. So previously it was just that you have S minus M square, and then you have U, and then you just have the rotation or the projection down is only from the U minus M square. But now you have U minus M square, plus you have another additional polynomial. The polynomial is different, so there's an additional G rotation. So it might not be, okay. So it might not it still might not be complete. Okay, we'll see how this thing develops. You can decide at the end whether we split this into two or we put it into in terms of like one big thing.
Yeah.
Okay, so Hasan, did you? But I guess you still haven't put. Have you imposed further constraints yet?
No.
Okay. So maybe, so Hasan, can you just verify that you reproduce the photon? And
Okay.
I guess you can see, I mean, so I mean, we can show, I mean, we did this analysis before, but I think that maybe let me just share screen. Yeah, so maybe let me just do let's see. Yeah, so because I remember that Z, they also mentioned this in their paper.
Chapter 5.
Yeah, so this is minus minus plus plus. I think they talked a little bit about.
I think they talked about the minus plus plus minus after their graph. So it's further back.
So it's probably further down.
Yeah. Yeah. Something somewhere.
Yeah, good. Yeah, it's this one, right?
Yeah.
Yeah, I did. Okay, I guess they just say that it's because the minus J. Yeah. Yeah, so they say that you're not supposed to derive bounds. So yeah, that'll be interesting. Yeah, maybe we should clear. I mean, one thing is to verify that this is the same. This is the same. I guess you could. I mean, I guess it's easy to see that you guys are working with the same things, right?
Mhm.
Mm,
I mean, they're doing D4 minus 4. I mean,
yeah.
Yeah,
and this is the same thing with you guys. So they're saying that there's no bound. So and that's what we saw at the time before as well. So yeah, maybe you guys can, I mean, one of the things to make sure, because make sure. Oh, but you're already saying that you're reproducing these types of plots, right?
The tables for.
I mean, this kind of
Yeah,
plot, right?
this one, the red one.
Yeah, this
but
is.
the red one is without using the other.
Yeah,
alphabet.
this is really mysterious. There's something very weird about this. Okay, I know. I mean, first, I mean, of course you can just, I mean, sorry, I mean, just stupid, right? I mean, you could just do SDP, right? Now you can just do SDP just on that amplitude. Right? And see if you carve out anything, if it's bounded or not, right?
But we don't
Uh,
have any null constraint, but STVB I think requires null constraint to work.
yeah, I'm not sure.
Yeah, we can try. Mm.
Yeah, that's true. Yeah, that I think maybe it's just saying that, let me think, what does it, so the no. Okay, I think it's very easy to see, right? So all you need to do is just, so you have this region, and then you guys are saying that some regions are being thrown out.
Yeah.
Right? So you can just test, right? You can just look at some of these. I mean, at least numerically, you just do find instance. Look at the region where it is being carved out, and then do find instance for the mixed things and see if it can find actually a solution. Because I guess what you're saying that those points that are being ruled out don't have a solution in the mixed one.
Yeah.
So we're finding spectrum in this way.
I guess your guys, and then maybe you can understand a little bit why you cannot find. I mean, why is there that then you're saying that why is there some points, some. I mean, so one statement is that as you say that for minus plus plus minus any point should have a spectrum that is associated if it's unbounded, right? If it's unbounded and minus plus plus minus any point should be
Given by some spectrum.
yeah, but maybe as a first level check just to see what is going on. find a point that is being ruled out, and then look into the minus, plus, plus, minus, and see if indeed you cannot find a representation that generates that point. If you find that indeed it does not have any representation that generates that point, then that means that indeed it is actually a bounded space. And then we can understand why is it a bounded space. So this will be something very true, right? You're just looking at some point that is outside, that is in the region where you carved out, right? Take that point, translate that point into which EFT coefficients it corresponds to in the minus, plus, plus, minus sector. And then see why is it that the minus, plus, plus, minus cannot generate that point. If we have an understanding, then I think we're starting to get a feeling. First, this will allow us to see if there's actually some code issue that we misunderstood and the code is not doing the right thing. But if it's not the code issue, yeah, then we should use this and we should generate, this will help us to understand why is there actually a boundary. And maybe then indeed, then SV is wrong. There's actually a boundary, that'll be cool. Yeah, I think that we need to make sure that we know what we're doing it before we move on to higher K. But we should definitely move on to higher K and then maybe also combine with what Laurentio is doing. Yeah. Okay, sorry to so let me just mention one thing. I want to develop it a little bit more. I know that I know that there's these all these various things. I'm going to talk first off for the machine learning. I know that Fishbone is interested in the machine learning, so I'm going to talk to Miranda. So she says she has some idea. I'll talk to her next week a little bit about whatever her idea is, and then I'll relay, and then we can discuss a little bit more. But yeah, I'm very sorry that I keep having like crazy ideas that I wanted to explore. So there's another crazy idea. So I just want, of course, we're all busy. So but another crazy idea is that, of course, one of the things that so this is okay. So here's the following statement. So one of the things that, of course, that sorry. So let me take one step back. So this will be just a two-minute blah blah. So we know that actually S matrix, this S matrix bootstrap is very different from CFD bootstrap in the sense that CFD bootstrap, we in principle know that the 4-point function and the OPE, these are all you need to know about the theory, right? Because then the higher point functions can be obtained from the lower point just by these OPE. You just bootstrap it up. So in principle, I think that the higher point doesn't really impose any constraint on your theory, because all of your OPE coefficient, that is already contained in your 4-point function. But of course, this is not true in amplitudes. There's a lot of information in the higher point amplitude. So of course we can ask, why are we not doing bootstrap for higher point amplitudes? Doing this kind of analysis, STP, blah, 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 so and so forth. And of course, the answer is very trivial. It's a practical problem, right? It's just that higher point, you have more number of kinematic invariants, so the functions are more complicated. The discontinuity and stuff are more complicated. However, there is something interesting at 6 point, which might be able to. So it's about the probably I know Fishbone and Hudson haven't heard about this before, but it's really about shock waves, which is something that one initiated this whole discussion by Maldacena and Zabotov and collaborators, and so shock waves is a gravitational solution. So it's like a shock wave. It's just that it's a graviton pole. Oh, sorry, it's not a graviton. Sorry, it's a gravitational solution. So it's like a black hole solution, except that it's not spherical symmetric. It's really like a line. So it's like a wave that is propagating. And in the old days, so they were talking about 2 shock waves, and then they're talking about 2 shock waves. So in the original causality constraint, it was really talking about 2 shock waves it's talking about 1 shock wave, and then the particle comes in, it hits the shock wave, it's going to be shifted and it's going to come out. And so it's talking about the time delay associated with this entire process. later on, Sasha had this interesting paper about then you have a non-trivial constraint if you consider two shock waves and a particle go into two shock waves, and the particle going into two shock waves, you want to have a non-trivial constraint where it's independent of which shock wave it goes in first. So it's like if you have T1, T2 being your shock wave, you have T1, T2 have to be the same thing as T2, T1. This process. So it's independent of which one it goes through. So in other words, the shock wave can commute with each other, and the process should be the same. So okay, so here's the punchline. So the punchline is that I think that the shock wave, essentially you can, and because I mean it's really okay. You know what? Why don't I just show the maybe I already have. So I'm working through this, but I believe that I believe that this is actually a 6-point process. But of course, there's a special kinematic configuration for the 6-point. So I'm working. Yeah. So this is the picture that you have. So you have a. So you see you have a P4 and P3, and this is the shockwave graviton. So this is GP1 and GP2. And so you can see that this almost looks like a 4-point scattering, right? But then the point is that P1 and P2, of course, these are off-shell gravitons. They represent the shockwave source. And so yeah. And so the point is that that for consistent theory, these two shockwaves have to commute. So which you can see that this is the story. Yeah, so the result does not complete on the shock ordering. So that means that there's a compute. When there's a commuting thing, that means that there's a null constraint, right? Now, of course, this is not an amplitude. We're saying that this is not an amplitude, but so I'm saying that you can actually source this kind of shock by using so instead of this instead of having this thing coming in as an off-shell thing, instead of having, sorry, where's the picture? Yeah, so instead of, so of course, you might say, but the problem is that this is not an amplitude. This is a shockwave configuration where you Fourier transformed it. So this is strictly speaking not a 4-point amplitude. But this is, however, actually a 6-point amplitude, because you can consider the limit where this is so this is coupled to the source that emits this shockwave graviton. So you can think of there's another source here, and then there's another source here, and then this will be a 6-point amplitude. And the reason I say this is because some of you know that I've been doing black holes for a while. And so for black holes, I mean, like, for example, the way that we describe in scattering amplitudes, the way that we describe black holes is that you have some source that is emitting a graviton, and the source have particular couplings with this graviton, such that when you feel this graviton, it's reflecting the fact that this source is a black hole, it's a Kerr black hole. So that's how we are doing this. And so I thought that, and there must be, and since these are just classical solutions, so there might be some similar descriptions, and just like that, in which you have this things here that is sourcing the shockwave graviton. And so I looked through it, and I remember I read something about somebody that did this. Indeed, somebody actually did this. So this is someone from MBI. Who wrote down the gravitational shockwave as scatter. So it's, I mean, I mean, of course, this is, if you're interested, this is just developing, reviewing what is a shockwave. But the point is that it's also using this kind of 3-point coupling to source this shockwave source. So in a nutshell, so basically, I think that it'll be, yeah. So I think that we have another kind of bootstrap sitting here, where we can develop, which is we can translate this kind of shockwave commuting constraints from gravity into yeah. So of course, this still, I need some time to really go through the details, but yeah. So this just to let you guys know, I'm thinking about something like this, and maybe, I mean, of course, there's news, as you guys are feeling, there's too many things to do. So hopefully some of the students can join us, and then we can all look in. look in. It'll be fun to understand all of these various things. But yeah, this is the thing I've been thinking about actually today. Okay, so maybe you guys first, and you guys can make sure that the things, I mean, just the various set, and then Laurentio, you can just update the note, just more pedagogical, as if you're writing a paper on this, and then let us know when you're done, and then we spend a day or two reading, and then we regroup again.
Yep.
Yeah. Okay. All right. Thanks, guys.
Okay.
Thanks.
Okay. Have a good. See you. Bye.